Okay, here we are going to look at some u-substitution integration problems that are very straightforward. And I'm going to say they are so straightforward that I hope that by the end of this lesson, you're comfortable skipping the substitution and simply writing down the answer with no work shown. And so our very first example, I'm going to actually work out the long u-substitution method where I see cosine of 5x. I think the 5x would be a good choice for the u. And before I do anything else, I have to account for du. So the derivative of 5x is 5 dx. I want to see 5 dx in the problem. I don't see it yet. However, I could squeeze a 5 in there with the dx, and I put a 1/5 out here. And now we are clear to substitute. So it's 1/5 antiderivative of cosine of 5x will become cosine u, and the 5 dx is du. And at this point, I have a very nice recognized antiderivative of cosine u du. The antiderivative of that is sine of u. I'm going to go ahead and plug my u, which is 5x, back in, and it's times 1/5, which I'm going to write as sine 5x over 5 plus c. So that is not a very difficult u-substitution problem. However, all of that stuff that I wrote right here, all the steps right here, could be avoided because this is a very, very common setup for antiderivatives. And I want you to recognize some of the patterns and what happened with the integral and how the final answer cleaned up. And so let's look at that one again. And if you look at it, you'll notice that it's almost a recognized antiderivative. If this 5 was not here, if that 5 was not here, then the antiderivative of cosine x is sine x. Okay. Now the pattern I want you to recognize in that work we just did is that if you have a recognized antiderivative, an almost recognized antiderivative, and the only thing keeping it from being straight up recognition is there's a number in front of that x. You could go through and do u-substitution and it wouldn't take that long, but it will always end up being sine of, you just keep that constant, and then you will divide by it in the end. Sine of 5x over 5 plus c, which is exactly what we ended up with here when we did the u-substitution. And the over 5, the reason we have that over 5 part is because if you were to do the formal u-substitution, you'll end up having the 1/5 in front to offset the constant you threw in there to make the du show up. And this setup for an antiderivative is frequent enough that I think it's worth memorizing this little quick approach so you can immediately spit out the answer. So looking at number 2, the antiderivative of secant squared of 7x. Well, without that 7, if that 7 was not there, hopefully you recognize that secant squared is the derivative of tangent. So the antiderivative of secant squared is tangent x. However, the problem was not secant squared of x, it was secant squared of 7x. So all we do is we keep that 7 and we divide by it. There we go. Let's look at a few others, and they're going to be quick. We're not going to go through the formal substitution. Now 4 may be a little bit sneaky. Why are these out of order? Move over. Okay, so 4 may be a little bit, or 3 is a little bit sneaky. 4 is a little bit sneakier. 3, if that over 2 was not there, if that were just e to the x, the antiderivative would be very easy. And you may need to rewrite this to make the constant a little bit easier to see. This is e to the 1/2 x dx. Now, without that 1/2, if that 1/2 was not there, then the antiderivative of e to the x is just e to the x. Right? However, there was a 1/2. And so we keep that 1/2 and we will divide by the 1/2. You keep the constant and then you divide by it plus a c. Now dividing by 1/2 looks kind of dumb to me, so I'm going to rewrite that as e to the 1/2 x plus c, and there's your answer. So moving on to number 4, this one is one that is not as easily recognized for some students because you never took your time to learn your inverse trig derivatives. However, you should know that the derivative of inverse tangent x is 1 over 1 plus x squared. And if I didn't have this 6 in the problem, I have 1 over 1 plus x squared. So the antiderivative of this is going to be the inverse tangent of x, but there was a 6 in front of the x. So I'm going to keep the 6, we'll divide by it, and put a plus c in the end. There we go. So very quick antiderivatives. If you can recognize the patterns and recognize these memorized antiderivatives, it's that easy. It's very, very, very quick. Now a generic setup for these, f prime of ax, if that a is not there and you want the antiderivative of f prime of x, well, f prime is the derivative of just f, but there was an a there. So we'll keep the a and we'll divide by the a and put a plus c. And that really is the formula we're using for all of these antiderivatives. If it's almost recognition and the only thing keeping it from being recognition is a number in front of the x, this is the pattern that we're using. And I want to do two more really quick. I'm going to make one up on the fly, but for number 6, this one I wanted to do because a lot of people get the right answer, but for the wrong reasons. The answer does end up being negative e to the negative x, but it can be a little bit, not plus c. It can be a little bit deceiving because the derivative of e to the negative x is also negative e to the negative x. And I want you to think of this not as negative 1 times e to the negative x, but if we follow that pattern, this is e to the negative 1x. So it'd be e to the negative 1x. We keep that constant, and then we divide by the negative 1. And so while the answer is negative e to the negative x, you need to realize that the reason that e to the negative x is negative, the reason that negative is there is because we actually divided by negative 1, not really multiplying by negative 1, although there's almost no difference whatsoever. And then I want to make one more point, and I should have had this one pre-made, but I didn't think about it until I was doing like problem number 3. But let's say I had the antiderivative of the sine of 4x plus 3 dx. Now this one's a little bit uglier because it's not just sine of 4x. I put another number in there. I put a 3 in there. However, the inside is still a line. It's a linear argument for sine x. So that's linear. And linear just means that if you were to graph y equals 4x plus 3, that's a line. So if the inside is linear, so if you're really good at memorization and you're comfortable with the stuff that I just did on the first 6 problems, you can actually extend the rule to include anything linear. So if it's recognition, and the only thing that keeps it from being recognized is the inside is a line, then we could still follow that same pattern. The antiderivative of sine is negative cosine. We keep the entire argument the same. We do not change the inside, but we will divide by the constant in front of the x. And so it actually extends to anything linear. Doesn't have to be just a number times x, but anything that's linear can work. If that last little bit confuses you, then just forget it and do u-substitution for these. However, I do think that these first 6 where it was just a number times x is easy enough to memorize that it's to your advantage to do that.